All right, welcome back to Calculus. Today we're going to talk about our two normal applications of differentiation, but here in light of the chain rule. So remember, we do a lot of this. We want to find the equation of a tangent line. That's one of our major applications for this chapter. And we also want to find where the location of any horizontal tangent lines of a function, of the graph of a function. But today we're going to do this in light of the chain rule. Both of our functions are composite. So remember, if we want to write the equation of a tangent line, we need a slope, which basically means we need to evaluate to find the slope here at x equals 3. We need to evaluate f prime of 3. That's going to be our slope. Simple enough. Okay, so we need to find f prime. So f prime of x is going to be, okay, notice we have a composite function. So let's first always identify the inside and outside function. Okay, the inside and the outside. What's the outside? That's going to be what? X to the 1/2 power, the square root of x. And the inside function is x squared plus 7. Okay, so now we can apply the chain rule. The chain rule says you take the derivative of the outside function. So this is going to be, according to the power rule, 1/2 times, okay, x. But instead of writing x there, I'm just going to put some empty parentheses in light of step 2 of the chain rule. So 1/2 times x, empty parentheses, times the, raised to the original power minus 1. So 1/2 minus 1 power. That's step 1. Step 2 is to evaluate that derivative at the inside function. That is, plug in the inside function. So x squared plus 7 gets plugged in. Step 3 of the chain rule says you multiply by the derivative of the inside function. So that's exactly what the chain rule tells us. The last thing to do here is just to differentiate x squared plus 7 and do any simplification that's necessary. So let's see, we have 1/2, and then that's going to be x squared plus 7. 1/2 minus 1 is negative 1/2 power, times the derivative of x squared plus 7. So we have, the sum of two functions. We differentiate those individually. So the derivative of x squared is 2x. The derivative of 7 is 0. So we're just multiplying by 2x. Now, of course, we want to write this without negative exponents. So we have a negative exponent here, so that's going to put a 2 on the denominator, then an x squared plus 7 to the 1/2 power on the denominator, and then that leaves me with just a 2x on the numerator. Okay? Now, that's our derivative, and we need the slope, which means we just need f prime of 3. So the slope is going to be our m for the point slope form is going to be f prime of 3, which means you have what, 2 times 3 over 2 times 3 squared plus 7 to the 1/2 power, which is what, 2 times 3 is 6 on the numerator, then that's 2 on the denominator. What, 3 squared is 9. 9 plus 7, okay, that's 16 to the 1/2 power. So that's what, times 4? So 6 over 8, which is what, 2/3? 6, not 2/3. Divide the top and the bottom by 2, you get 3 over 4. So there's our value of the slope, m. Okay? Once you have your slope, we just need a point now. So if we have x equals 3, then what's the point? So we have 3 comma what? Now remember, you go back to the original function to find this y value. If you plug in a 3, you get 3 squared is 9, plus 7 is 16, so 4. We have a point 3 comma 4. Okay? So now we have a point, x1 and y1. We have our slope, m is 3/4, And now all we have to do is plug in to y minus y1 equals m times x minus x1, then simplify it. So y minus y1, so y minus 4 equals m 3/4 times x minus x1, which is 3. And that is the equation of the tangent line, but we're going to write it in slope-intercept form, which means we need to add 4 to both sides and then collect like terms. So we have what? 3/4x. If we multiply by distributing 9/4 plus 4, is that right? Yeah. So we just need to do a little one last simplification. Ooh, 3/4 x. Okay, what? 9/4 plus 4. 9/4 would be 9/4 plus 16. Negative 9/4 plus 16/4, which would be what? Plus 7/4. Is that right? We get a common denominator. It would be like what times like 4/4? Yeah, and then that'll be 16. 16 minus 9 would be 7. Yeah, that's right. So this should be good. Let's check ourselves. Here, I'll get Desmos. So the original function was f of x equals square root x squared plus 7. And we had the point 3 comma 4. And we said our tangent line equation was y equals 3/4x plus 7/4. Looks like we have a winner. All right, so the red is our curve. To be honest with you, I had no idea what the square root of x squared plus 7 looked like. It's not one of those standard curves that you memorize in any class, but there it is. And there is the point, 3 comma 4. Okay, and here is our tangent line. Notice that's exactly what you'd expect. It just barely grazes the curve at that single point. And again, we think about these as a linear approximation. That is, if you really zoom in on this point, you can't tell a difference between the line and the curve. The green and the red, they line up perfectly. Not perfectly, very, very close though. As long as you're very close to that point. That's why it's called a tangent line approximation. Okay, because the line, the green tangent line, basically approximates the curve very, very nicely as long as you're close to this point 3 comma 4. Now, of course, if you get far away from this point, the tangent line, the green line, does a terrible job approximating the red curve. But if you're really close to 3, x equals 3, then this line does a very good job of approximating the curve. We say that as long as you're within, like, it's called the neighborhood of 3. A neighborhood is like a really close open interval around x equals 3. Okay, so that is our tangent line example using the chain rule. Now let's do an example where we need to find some horizontal tangent lines. Perhaps if they exist, of course. You're not guaranteed they exist, but we can do our best. Okay. Remember, what is our what's our method for that? Our method is to set the derivative equal to 0 and solve. So we need to solve the derivative g prime equals 0. Now this is interesting. Look at this one. I mean, it's exponential times a trig function, and it's composite. So what I'm seeing there is I see two composite functions multiplied together. So we're going to need to use the chain rule, but first we're going to need to use the product rule. So let's hop right in and calculate g prime. So g prime is, according to the product rule, you take the derivative of the first function, e to the pi x, then multiply by the plane second function, cosine pi x. Then we're going to add the derivative of the second function, which is cosine pi x, which is also composite, times the plane first function e pi x. Okay. Now, both of these individual derivatives are going to require the use of the chain rule. So let's tackle e to the pi x first. What's the inside and what's the outside function? Okay, inside and the outside function. The inside function is pi x. The outside function is e to the x. Okay, here, that's a little too close. Let me rewrite that. The inside function is pi x. The outside function is e to the x. That is, if you take pi x and you plug it into e to the x, you get e to the pi x. So that's our inside and outside function. Now, let's apply the chain rule. The chain rule says you take the derivative of the inside function. Sorry, wrong. It says you take the derivative of the outside function. So what's the derivative of e to the x? Well, lucky us, it's e to the x. That's your super easy derivative. So there's the derivative of the outside function. You then evaluate it at the inside function. So instead of an x there, you plug in the inside function and you write pi x. But then the chain rule says you multiply by the derivative of the inside function. What's the derivative of the inside function? The derivative of pi x. Remember, pi is just a constant. So we have constant times a variable. You can factor out that constant multiple, and you have pi times the derivative of x, which leaves you with just pi. So times pi. Of course, times the cosine pi x that was there already. Plus, okay, now we need to take the chain rule derivative of cosine pi x. So let's identify the outside and inside function. So the inside function, again, is pi x. In this case, the outside function is cosine x. So the chain rule says you take the derivative of the outside function. So the derivative of cosine is a negative sine. And then the second step of the chain rule says you evaluate that function, that derivative, at the inside function, which is pi x. And then the third step of the chain rule is to multiply by the derivative of the inside function. But notice, our inside function is the exact same it was for the first derivative. So the derivative of pi x, you can factor out the pi, take the derivative of x, which is 1 times pi. So we multiply by pi. And then times e to the pi x, just like that was there according to the product rule. There's g prime. We could factor it a little bit, since we're going to have to do that anyway in just a sec. What do both terms have in common? They both have a pi, and they both have an e to the pi x. So we can factor out a pi, and we can factor out an e to the pi x, leaving us with cosine pi x plus a minus, so minus sine pi x. There we go. Cool. Okay. Now what can we do here? Okay, that's our derivative. And now, the key to finding horizontal tangent lines is to solve g prime equals 0. So g prime equals 0. So our derivative is pi times e to the pi x times cosine pi x minus sine pi x equals 0. Well, that looks kind of nasty, but it's factored already at least. Remember, if you have a factored expression set equal to 0, you can set the individual factors equal to 0 using that zero factor theorem, or the zero product property from algebra. So we have 2 factors basically. Well, actually, first, if it makes you feel better, you can divide both sides by pi. since pi is a scalar, you can divide both sides by pi, and then you get e to the pi x times cosine pi x minus sine pi x equals 0. So we got rid of that scalar. But now we just have two factors, two variable factors equal to 0. We can set them individually equal to 0. And so we get either e to the pi x equals 0 or cosine pi, not pi by itself, cosine pi x, or cosine pi x minus sine pi x equals 0. So we'll have horizontal tangent lines at the solutions to those two equations. Now, first one, let's tackle it. What does this imply? E to the pi x equals 0. Here's a common situation we'll have, just like this, and here's the response. No solutions. Why? Think about the graph. E to the pi x. What does that graph look like, and what are we actually trying to solve for when you're setting a function equal to 0? When you're trying to set a function equal to 0 and you solve, what you're finding is the x-intercepts. So we can ask ourselves, what are the x-intercepts of that function? But if you know the graph of that function, then you know there are none. E to the pi x has a y-intercept of 0, 1, and it looks like this. It has a horizontal asymptote at the origin. It never crosses the x-axis. There are no solutions. So e to the x, or e to the pi x, or e to the ax, for any real number a, has no solution. Now it is possible for exponentials to have set equal to 0 to have a solution if they're shifted up or reflected and kind of some weird stuff happens. But if it's just a very basic exponential set equal to 0, it's not going to have any solutions. Okay, unless it's been, again, translated, transformed somehow to where it forces an x-intercept. So there's no solutions to this first one. Okay, so no solutions here, but there might be solutions here for that second equation. Let's see, and we've had one similar to this. This is composite, so it's a little different, but here I would recommend that we instead consider cosine pi x equals sine pi x. Usually you do want your trig functions on one side and 0 on the other side, but I think when you have this situation, it's easier to think about it when you have them set equal to each other. Now, we actually did a very similar problem a few videos back. But here, since we have a composite function, what I like to do is use what's called substitution. That is, we want to solve for x. We have a pi x. But what if I did this? Let's just say u equal pi x. Okay? So then we could say cosine u equals sine u. We can solve for u now without the composite business using our unit circle. Then we can come back and solve for x at the end. So basically this is saying where's cosine equal to sine? And we did this problem a little while ago. If you think about your unit circle, where does sine equal cosine? Oh, you know what? I did not specify an interval, so I need to specify an interval up here, and I'll do this before you get these notes. I'll fix them. I'll add the instructions and re-upload them before you ever see it. But I need to specify an interval. So I'm going to say let's solve on 0 to pi. So on 0 to pi, since that is pretty that's pretty customary, 0 to pi. Otherwise, we're going to get an infinite number of solutions here. Okay, So on 0 to pi, well, we know in our unit circle, let's see how bad of a job I do in the unit circle this time. Oh, pretty bad, but it gets the job done, I guess. If you think about your unit circle, at pi over 4 here, the coordinates of that point are root 2 over 2, comma root 2 over 2. You know, the cosines, the x value, the sines, the y value. In other words, they're equal. Likewise, at this angle over here, that point has coordinates negative root 2 over 2, comma negative root 2 over 2. In other words, they're equal. Now, this angle is pi over 4. And then we have this angle is what? Okay, pi over 4. Then we have 3 pi over 4. Then we have 5 pi 4. So if we're only looking for solutions in 0 to 2 pi, then we have those solutions. Now, if you look at a different interval, well, then you'll have different solutions because this is going to be periodic, and we're going to have different solutions based on the interval of interest. But here I said, let's focus on 0 to pi. Or you know what? It might be better to focus on negative pi to positive pi, depending on how, because this function is going to get crazy probably for big values of x because of that factor there. It doesn't really matter. I mean, it doesn't really matter what we use here. I guess we can stick to 0 to 2 pi. But now we're not done yet because those are solutions in terms of u. So u equals pi over 4, and u equals what would you say, 5 pi over 4. But those are solutions in terms of u. We want solutions in terms of pi. And so what we do is, okay, if u equals pi x, then we say, okay, let's back substitute for x. We get pi x equals pi over 4, and we get pi x equals 5 pi over 4. And if we solve for x, that gives us what? Divide both sides by pi, and we get x equals what? 5 over 4. And we get x equals, oh, we're kind of squeezed here, but x equals what? 1/4. I just realized whenever we do this substitution, I don't always forget this, but I do forget sometimes. Whenever we do substitution, it's best not to stop considering solutions. Like if you're interested in 0 to 2 pi, well, you might want to consider more initial solutions in terms of u. Like what do I mean by that? I mean that okay, pi over 4 is an answer, but what about a coterminal angle? For instance, what about, okay, 2 pi plus pi over 4 is what? So 2 plus 0.25, that's 9 over 4. 9 pi over 4 is a terminal angle. Now, I'm just kind of thinking out loud here. So 9 pi over 4 is a terminal angle. Now, clearly 9 pi over 4 is not in 0 to pi. However, we're solving this is in terms of u. I'm going to have to set this equal to what? U is pi x. So if I set it equal to pi x, once I divide by pi, I might get solutions in 0 to pi. So x equals what? 9 over 4. Well, is 9 over 4 between 0 and 2 pi? Well, let's see. Well, yeah, I mean 2 pi is 6.28, so 9 over 4 is 2.25. So yeah, I mean that's another solution there. I didn't think about that, so I probably need to think about that and add some solutions here. So because that's another solution. we're going to have, in fact, a good number of solutions like that. Okay, because we're dividing them all by 3 essentially. So I guess the one way to fix that, and maybe I'll do that instead. Maybe instead I'll say, hey, what about solutions in 0 to 2? That's probably a better way to think about this, because pi x, what I've done is I've affected the domain here. So let's do that instead. That's an easier fix. Let's look for solutions in 0 to 2. Because remember, what is the domain of pi x? What is the argument pi x doing? That's affecting the period of the function. So the way you find the period of cosine is the default period is 2 pi. But if you have a scalar multiple on the input, then you divide 2 pi by that scalar. So 2 pi over pi is 2. So now the period of this cosine function is 2 instead of 2 pi, which that means, yeah, then, okay, now I can stick with my original solutions, 1/4 and 5/4, because now 9/4 doesn't fit in this interval of interest. That's probably the best way to go about this. I'll amend the instructions to go like that. Okay, that makes more sense. That way we only have those 2 solutions. We don't have to worry about looking for more. But that is something to consider. What I just mentioned, that is something you need to consider when you are using substitution to solve trigonometric functions. Now, let's look at this function. I have a feeling it's going to be a crazy function, because that e to the pi x is going to make this get really big really fast. E to the pi x times cosine pi x, yeah, crazy. All right, g of x. So notice how I said let's go from 0 to 2. Well, notice how it's going crazy up and down. Okay, think about this. It has to come up. There is no discontinuities here. See, these aren't asymptotes. So so this function's going up, then coming down. So it has to have a horizontal tangent lines all over the place. Now I said let's consider from 0 to 2. So 0 less than equal to x less than equal to 2. So we're just considering that little section. And let's see. Okay, there's a horizontal tangent line. See, there's a little trough down there. Didn't we say that 5/4 is a solution? I think so. Yep, 5/4, 1.25. And then let's zoom back in, and there we go. There's another one. We said that 1/4 was a solution. Yeah, 0.25. Okay, so yeah. And again, if I didn't have that restriction, I have to have a restriction, because otherwise, there's another one, and there's an infinite number. Now, it's really hard to tell over here to the left as we approach negative infinity, but notice here there's barely a peak. There's barely a peak right there. Now that's an x-intercept, but there's barely a peak there, and it's getting very, 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 very low y values, whether positive or negative, very small y values, but it is ever so slightly oscillating. So there'll be an infinite number of peaks and valleys, horizontal tangent line locations to the left as you approach negative infinity, but also to the right though, there's getting crazy oscillations, way up and way down, because of this factor right here. Okay, but again, what we decided to do on the fly, at least, was only consider 0 less than equal to x less than equal to 2 to 2, and we found those nice 2 solutions, 1/4, and then there was a 5/4. And remember, graphically, folks, remember this. Graphically, we can verify this by considering g prime of x. And notice g prime of x has an x-intercept at 1/4, which means there's a horizontal tangent line slope of 0 on the original function at x equal 1/4. Also, there is a x-intercept on the derivative function at 1 1/4, which means there is a horizontal tangent line on the original function down here, way down here at 1 1/4. Okay, so always be sure to really stress that connection between the graph of a derivative and the graph of the original function. Also notice where the graph of the derivative here is positive between 0 and 1/4, that means the original function is increasing over that same domain. Notice that the graph of the derivative is below the x-axis from positive 1/4 to positive 1 1/4, which means the original function, the purple function, is decreasing over that same interval. Okay, so where the original function is decreasing, the derivative function is below the x-axis. Where the original function is increasing, the derivative function is above the x-axis. Super important connection there. All right, so those are our two examples for today's video, finding where we have horizontal tangent lines, as well as finding the equation of the tangent line, both using the chain rule. If you have any questions, don't hesitate to reach out. See you soon.